Greetings again, ladies and gentlemen. Welcome to your Midterm 2 exam review for next Tuesday. You should be able to find the exam review notes on the review page as well as in the course files. So please download them, open them up in a window, whatever you got to do, and follow along. To begin with, our first topic is going to be atoms. What are they? What are they made out of? Atoms happen to be the smallest form of any given element. What distinguishes an element, of course, is the number of protons in the nucleus. Hydrogen has 1, helium has 2, and so on. Just the number of protons in the nucleus that denote what we call the atomic number. Now, of course, atoms are not the only thing that hydrogen and helium and gold and silver and whatever are made up of. All of these atoms typically also contain electrons, and most of them, with the exception of standard elemental hydrogen, also have funny things called neutrons. Protons are positively charged, electrons are negatively charged. Neutrons have no charge, no discernible charge. Protons have a high mass, about 1 atomic mass unit, or AMU. Electrons have about 2,000 times less. If you took 1 atomic mass unit and divided it by 2,000, that's about the mass of an electron. The neutron has about the same mass as a proton, about 1 atomic mass unit, or AMU. With those building blocks, you should be able to define the characteristics of just about any atom or molecule. Okay, let's talk a little bit about the phases of matter. How many are there? Strictly speaking, there are 4. There are 3 sort of common ones. We don't see a lot of the 4th one, of course, that's plasma. The other 3 are solid, liquid, and gas. And in the case of something like water, solid water, of course, is ice, liquid water is water, and the gaseous form of water, or water vapor, is commonly called steam. Now, in order for these things to change in between these phases of matter, you either need to put energy into heat, into the substance, or take it out of the substance. But more on that later. Let's talk a little bit about what temperature and heat are and what they do to substances. Generally speaking, we say that temperature is a measurement of the average kinetic energy of the particles in a substance, or how readily it wants to try to give this amount of heat, this kinetic energy, away to particles of a nearby substance, something that it's in contact with. The more kinetic energy a particle has, we say the higher the temperature. The hotter something feels, the more quickly it can transfer heat energy, say, into your hand or into your cup of coffee or what have you. Heat, then, has to have a similar set of defining characteristics to energy, right? And indeed, heat is generally referred to as energy. We even use the same SI unit of the joule, although sometimes we use the calorie because stupid historical reasons. Now, strictly speaking, if you take a substance and you apply heat to it and thereby raise its temperature, right? You increase the average kinetic energy of the individual particles in the substance. What happens to it, assuming it doesn't change phase? Like, if you heated up some water but didn't make it boil, what would it do? It would expand, right? Because the individual particles are moving around more, they're going to bump around more, and they're going to expand in total. And that's why things expand when you heat them. Now, there are several methods by which you can transfer heat into and out or out of a system and try to change its temperature. The 3 major ones, of course, are conduction, that's direct contact, right? If you take your spoon and you put it into your hot coffee, what happens? Well, by direct contact, the coffee is going to heat the spoon, right? The kinetic energy of the particles in the coffee are going to heat the spoon up, right, by direct contact, by transferring the kinetic energy of the coffee particles into the particles of the spoon. There's also something we call radiation, right? Like the light. And that, of course, gives off heat in the form of electromagnetic radiation, or light. Just like if you stand out in the sun, right? It's going to transfer some energy to you. There's another method, of course, by which heat can go from one place to another, and that's convection, like in a convection current. For example, let's say that you have
you've got a pot, right? And there's some water in it. The pot is on the stove, and so heat is being transferred from the, I don't know, electric stove, range stove, whatever you've got, into the bottom of the pot, right? So what's going to happen? Well, the water at the bottom is going to get heated up first, right? So let's say a bunch of heat gets transferred into this water here. Now it's going to expand, right? This water is going to expand. And as it increases its volume, it's going to decrease its density, right? And as a result, gravity is going to have less of a hold on the water that expands compared to this tiny little bit of water, say over here or whatever, right? The colder water is going to stay at the bottom, the hotter water is going to rise. And so as this water gets heated up, it's going to expand and rise up here to the top. And when it finally gets to the top, it's going to have essentially an infinite cold reservoir, right? There's going to be so much air here that's cooler than the water that the water is going to be able to release some of its heat into the air. That's going to cause this water to shrink back down, right? It's going to cool off, lose some temperature, at which point it's going to decrease its volume and then sink back to the bottom. And that's going to cause a cyclical current, right? The water goes up, goes back down. And it's going to cause a cyclical current that we generally call a convection current. Pretty simple and straightforward, right? Okay, let's talk a little bit about change of phase. If I can find what I did with my eraser here. Here we go. Now let's talk a little bit about the three common phases of water. Typically speaking, the three phases of water that we deal with on a day-to-day basis are solid, or ice, liquid, that's just supposed to be Q-U-I-D, and gas. There is also another phase, but we don't often come into contact with the plasma phase of water, not in our daily lives. So let's not worry so much about that. Now, if you have solid water or ice, if you apply some heat to it, what's it going to do? It's going to melt, right? If you take some heat out of it, so this will be adding heat, this will be subtracting heat, right? If we take some heat out of liquid water, it can freeze and become ice. If we add some heat to liquid water, it will boil, right? If we take our liquid water and we boil it, it then becomes steam or water vapor, right? Gaseous water. However, if we take some heat out of the steam or the gaseous water, it can condense back into liquid, right? Now, is it possible that some materials can go from solid to gas? Believe it or not, in the right conditions, water can even do this. But a more common occurrence is if you take something like dry ice, right, solid CO2,
At room temperature, it doesn't have a liquid, or it's at normal atmospheric pressure, it doesn't have a liquid phase, and so at room temperature it'll go straight from solid to gas. We call that sublimation. And of course, if you're heating up the solid, it has to absorb heat, or you have to put heat into it to make it sublimate to go to gas. And now it is also possible, of course, if you want to take some heat out of the gas to make it go back to solid, that's called deposition. And that is how we take carbon dioxide, say from the atmosphere or something like that. We freeze it, take a lot of heat out of it, cool it off to a very, very low temperature, and then it can become the dry ice that we use to keep our ice cold in our coolers and whatever. So that is how matter changes phase in between phases. Let's talk really briefly about thermodynamics and the laws of thermodynamics. The 0th law of thermodynamics says something like this. If system A, some block of metal or whatever, is in thermal equilibrium with system B, and system A is also in thermal equilibrium with system B, then that means system B is also in equilibrium with system C. This is the old algebra identity. If A equals B and A equals C, therefore B equals C. They call that the 0th law of thermodynamics. So we'll put a 0 there for now. The 1st law of thermodynamics, regardless of how Rick and Morty may have stated it at some point, or I guess a better way to say that is how Morty misquoted it in the 1st episode. The 1st law of thermodynamics actually says something like the heat supplied minus the work done by a system is equal to the change in internal energy. Now, an easy way to think of that is if you apply heat to a system, it's going to change the internal energy, unless it also does some work, right? So let's say you've got a heat engine, right? Some air conditioning unit or something like that. You apply some energy to the system, and it's going to give you some useful work out, right? But it could also store some internal energy inside the system. Now, if the system does no work, then what's going to happen is that the heat is just going to change the internal energy, right? And if the heat supplied to a system equals the work done by the system, then it won't change the internal energy of the system at all. That is the 1st law of thermodynamics. The 2nd law of thermodynamics it's typically stated something like this: the change in entropy in a system is greater than basically that the entropy in the change in entropy in a system is greater than 0 for a given temperature. Now, what this really means is that the entropy, or the amount of disorder in a system, always tends to increase, never decrease. And what this really means, if you want a physical interpretation, is that real processes in the real world are not reversible. For example, if you got a flu shot, right? The doctor or the nurse or whoever is administering the flu shot to you sticks a syringe into your arm and pushes the plunger down, right? If they pull the plunger back out, you're not going to get the flu medicine back, right? That's just so incredibly improbable that it will never happen in a quadrillion instances. You know, if there were an infinite number of parallel universes, that might happen in maybe 1 or 2 of them at the most. That's like putting a bunch of cats in a large warehouse and stashing a bunch of fish all over the place, and then expecting them all to come back into the same carrier that you brought them into the warehouse in. It's just not going to happen, right? Real processes in the real world do not have a reversible kind of property. They do not work in reverse. Okay, what is a wave? A wave is energy moving through a medium. If you want to talk about a sound wave, for example, that is a compression of air, right? That is energy moving through the air, and eventually, you know, it'll get to your eardrum and stimulate it, sending a signal to your brain that you interpret as sound, something along those lines. Let's talk a little bit about electron orbitals. If we want to talk about, say, the hydrogen atom, right? The hydrogen atom has one proton in its nucleus, and that means that the one electron that it has out in its ground state orbital, because these two particles have a certain amount of attraction towards each other, right? This is positive, this is negative, they attract each other. And because you're talking about a certain amount of electrostatic attraction, this electron can only live at certain places. Its ground state, what we call n equals 1, and then up here is n equals 2, and then n equals 3, and so on, right? Now these energy states are perfectly quantized. They're exactly the same every time. So much so that if you had, say, 2 protons, like in a hydrogen atom, the energy level here would be at a different place, and n equals 2 and n equals 3 and so on. Also, for them to be electrically neutral, there would have to be 2 of them, right? Now, why is this important? Well, the number of protons will obviously dictate the amount of electrostatic attraction that these electrons are going to have, causing the energy levels to be different. And if you remember, let's say some light energy comes along and stimulates this electron. Now, if it absorbs exactly the right amount corresponding to the energy difference in between these 2 energy states, it can get excited. But as long as there is any open space in this orbital here, it's not going to stay there very long because the lower state is more stable, right? It's closer to the nucleus. And as it does so, it's going to emit a photon corresponding to exactly this energy difference. Now these energy differences, of course, are going to be different. This was like where n equals 1 was for hydrogen. This is where like n equals 2 was for hydrogen. And this energy difference here is different from this energy difference here, right? These are 2 different energy difference states, and so they will emit 2 different photons or 2 different colors of light. And that's why when we saw the helium spectrum, which was like these transitions, this one, one from these 2 states, one from maybe these 2 states, right? These are all different from the colors that you would see in a hydrogen atom. And that's why if you excite a gas, generally the gases all emit different colors. Hydrogen, helium, mercury, neon, we saw a bunch of those. Oh, sorry, Lucky. I didn't realize you were leaning up against that. Hi, Lucky. Everybody say hi to Lucky. Try to keep this level here. Okay, let's talk a little about Hooke's law, shall we? Hooke's law says this: the force in a spring is minus kx, where k is this thing we call the spring constant, or the measurement of the overall strength of the spring, and x is the displacement from equilibrium. Now, there are 3 components to this equation. So if you were to get a physics problem with this in it, you would probably have 2 of them and have asked to be solved for the 3rd. Let's just work a simple example, shall we? Let's try to solve for this thing maybe. So let's say that a force of 50 newtons displaces a spring by 10 centimeters, or 0.10 meters. How big is the spring constant? Well, F is equal to minus kx. Oh, by the way, What does the minus sign mean? The minus sign means, so let's say this is the spring's equilibrium position, right? Let's say we stretch it out some distance, x, right, by applying some force to it. What direction is the spring going to pull? Backwards, in the opposite direction. So it was displaced this way, that means the restoring force, the spring force, is going to push it back this way. That's what the minus sign means, right? If you pull the spring outward, it wants to pull itself inward to compensate. If you compress the spring, it wants to push itself out. And I'm sure by now we probably all know how springs work. In any case, that's what the minus sign means. In the opposite direction of displacement from equilibrium. So, when we end up with a negative number, we'll know what that means. In any case, we know the force is 50 newtons. We know that the displacement from equilibrium is 10 centimeters or 0.10 meters. We want to isolate this, right? Okay, so if we just divide both sides by x, we see that k is F over x. Our F is 50 newtons. Our x is 0.10 meters. 50 divided by 0.1, that's 500 newtons per meter. And if you ended up with a different unit, then you did something wrong. This is the SI unit for spring constant. Okay, let's talk a little bit about fluid pressure, shall we? That is the pressure in a fluid. And if you remember, if you want to think about the pressure that you feel on your eardrum as you're diving to the bottom of a swimming pool or something like that, what does the pressure depend on? Obviously, gravity is the motivating factor for any kind of fluid pressure, right? But the density of the fluid is one thing. We're under probably a few kilometers of air pressure right now, right? But water is much more dense than air. As a matter of fact, 10 meters of water is equivalent to 1 atmosphere of pressure. In any case, the third factor is the height, of course, and I just hinted at it there. Obviously, if you swim down to the bottom of a swimming pool, the pressure on your eardrum is going to increase until it becomes really uncomfortable and your ears pop, right? So, fluid pressure depends on the density of the fluid. That's what the Greek letter rho is. Times the acceleration due to gravity, what we call surface gravity, times the height of the fluid column above the point that you're measuring the fluid pressure. So this is fluid pressure. Now, remember, if you want to talk about the total pressure, that's equal to the fluid pressure plus the atmospheric pressure. If you're outside a swimming pool, there's only the atmospheric pressure on your eardrums. But if you jump in the swimming pool, you've got the fluid pressure from however much water is above your ear, right? The height of the fluid column above your ear, plus the atmospheric pressure, because the atmosphere is still pushing down on the pool, right? Pretty straightforward, I hope. Okay, let's talk a little bit about the buoyant force. The buoyant force, or the upward force that an object feels when immersed in water, is equal to the density of the fluid times the acceleration due to gravity times the volume of the object. Now, if we want to think about this carefully here, we're talking about the density of a fluid times the volume of an object, right? So let's say you take, I don't know, this eraser, right? And you immerse it in water, right? You submerge it below the surface of the water. it's going to displace an amount of water equal to its volume, right? The volume of the object. Density is mass over volume, right? So we've got a mass over volume here, right? Times another volume. These should cancel. Mass times gravity, that's a weight, right? But we're talking about the weight of the fluid, or the water displaced, right? If you're talking about immersing something in water. And so, therefore, we must conclude that while, yes, by definition, the buoyant force is equal to the density of the fluid that the object is immersed in, times surface gravity, times the volume of the object itself. This is also equal to the weight of displaced fluid. In the case of water, of course, we're talking about the weight of displaced water. Make sense? Let's talk really quickly about Bernoulli's principle and what it means. Bernoulli's principle says something like pressure 1 plus 1/2 rho, rho V1 squared plus rho GH1 is equal to pressure 2 plus 1/2 rho V2 squared plus rho GH2. Now these terms probably look pretty similar. This one looks a lot like kinetic energy, and this one looks a lot like potential energy, right? And as a matter of fact, they are very similar. Let's see if we can figure out something that connects all of these together, right? So let's talk about the first term, pressure. Now pressure, we said before, is force per unit area, right? That's got units of newtons per cubic meter. Or, I'm sorry, per square meter. I'm crazy here all of a sudden. Newtons per square meter. Now let's look really closely at this. Now if we were going to say that this is somehow related to energy, right? Let us recall what the unit joule is. Joule is like mass times velocity squared, right? 1/2 mv squared. So that's going to have units of kilograms times meters squared per second squared. That's the same thing as newtons times meters, right? Because a newton is a kilogram times meter per second squared times meters. That gives us a joule. Now there's a couple instances, most notably torque, where if we multiply newton times a meter, we don't say it's a joule, right? Because we're talking about an amount of leverage. We usually just leave it in newton times meters. But if we multiply newton by a meter, we get joules, right? Okay, so what if we said newtons times meters divided by meters cubed? That's the same thing as this, right? That's the same thing as pressure. So this is like saying energy per volume, right? Everybody with me so far? So pressure is kind of like saying energy density per unit volume, right? Okay, now let's look at this term, 1/2 rho v squared. We've got 1/2, that's just the number, right? Rho is mass per unit volume times velocity squared. Wait a minute, mass times velocity squared, that's joules again, right? So that's the same thing as energy per unit volume. What about this term? We've got density times gravity times height. Well, mass times gravity times height, mgh, that's the same thing as energy, right? But this is mass times gravity times height divided by volume. So here, now we're also talking about energy per unit volume. Essentially, this is a continuity equation, or a conservation of energy equation per unit volume. So all of these terms are essentially energy per unit volume, if you want to think of it that way. Now, let's try to give you some kind of example. Let's say that you've got some water reservoir, right? And you just so happen to know that down here at the bottom, it's moving with a certain velocity. You're going to know what the pressure is because you know the height of the fluid column above it, right? And let's say that this water just decides to go upward. Now, it's going to exhibit a change in pressure, but it's probably also because there's a change in the heights. You should be able to figure out the new velocity, right? Continuity equation. There's also a very important consequence of Bernoulli's equation, and that is this thing, where you say area 1 times velocity 1 is equal to area 2 times velocity 2. What does that mean? Well, let's say you got a pipe, right? And it has a certain area, right? And water is moving here at some velocity. If the pipe narrows, right, where we have a smaller area, it's going to have an increased velocity. Now, I know that may not be the most intuitive of all things, but let's just look at these two units here, right? Area times velocity, right? That's area is meters squared. Velocity is meters per second. So we're talking about meters cubed per second, or velocity per unit time. Essentially, we're talking about how much water goes past this point, right? Volume per unit time. Now, what we're talking about really happening here is we're saying that because this is the same tube, the same amount of water has to go past this point per unit time as has to go past this point per unit time. The water doesn't just get to magically bunch up somewhere. If it slowed down like that, then this would have to like expand or something, and pipes don't just magically expand because we want them to, okay? So, long story short, if you have a change in the cross-sectional area of some kind of enclosure that has water going through it, the volume must change accordingly because the same amount of water has to be conserved. Make sense? Okay, let's talk really briefly about the heat required to change temperature and to change phase. For an object to change its temperature, you have to apply heat to it, right? Now, the heat required to make something change its temperature depends upon a few things. Obviously, the mass. The more of a substance you want to heat up, the more heat it's going to require, right? Also, there's this thing called the specific heat. And the classic example, of course, is the sand versus the water. Now, if you wanted to try to heat up sand at the beach, it's going to conduct heat very easily. And indeed, if you go out to the beach and you sit there for a couple hours after sunrise and you take your shoes off and try to run across the sand, it's going to burn your feet. However, if you try to stick your feet in the water, it's going to be really cold, especially, out here like at the beach at Santa Cruz. It's cold year-round, even in the summer. Why is that such the case? Well, the sand has a smaller specific heat than water. Water takes a lot more energy to heat up, and that's why they say a watch pot never boils. It takes a long time because water has a really high specific heat. Okay, the third thing, of course, is the magnitude of the change in temperature. The greater the change in temperature, the more heat you're going to have to supply. Pretty straightforward, right? Okay. Now, if you're talking about changing phase, the heat required to melt some ice depends upon the mass of the ice that you're trying to melt, multiplied by the heat of fusion, or the latent heat of fusion for ice. Or, the amount of heat per unit mass required to heat ice. That's what this latent heat of fusion is. Okay? Obviously, if you're talking about freezing water and making ice, you're talking about taking this amount of heat out of the system, or adding a negative amount of this heat to the system, if you want to think of it that way. Similarly, the heat required to vaporize water or some other substance depends, of course, on its mass. The more water you want to boil, the more heat you're going to have to supply. But also the heat of vaporization. Now for water this is really, really high, which is why if you use evaporative cooling to try to cool somebody off with a little spray bottle if they're getting heat stroke or something like that, it is very effective. We're not in danger of that right now. We're kind of in the middle of colder weather, but if this was, say, the middle of the summer and you were trying to keep cool, the evaporative cooling is an excellent strategy. Okay, now we've already talked a little bit about convection, conduction, and radiation. We also talked a little bit about the heat engine, right? We said already this is actually just a restatement of the first law of thermodynamics, where the heat supplied to a system minus the work that the actual system does is equal, to the change in the internal energy of the system. Now for something like a heat engine, there was a certain maximum amount of efficiency that the heat engine can have, and that depends upon a couple of things. The efficiency is equal to the difference in between the temperatures that it runs at, T hot minus T cold, divided by T hot, because this is where it's getting its energy from. Now you have to be really, really careful with this. If you're going to use this kind of equation, this kind of expression, in order to try to figure out the efficiency of a heat engine, what's the proper unit to use? Can you use Fahrenheit? How about Celsius? Well, there's a problem with that, right? What if you run at a sub-zero temperature? Then you're going to have a greater than 100% efficiency. That's crazy talk, right? That's impossible. So the right kind of scale to use in general for any thermodynamic expression, any thermodynamic calculation, is to use the absolute temperature scale, or that which we call Kelvin. Remember? Because at 0 Kelvin is the temperature we call absolute zero. And if we use this absolute scale, we can't get ridiculous results, counterintuitive results, things like engines that have over 100% efficiency. Okay, really, really briefly, our last piece of information here. The wave speed is equal to the frequency times the wavelength. Oh, there's a lucky meal. Now the example that we used for that in this week's lecture was, let's say that you go down to Santa Cruz and you're looking at some part of the old broken down pier that a seagull is sitting on, and waves are coming and lapping up against it. And from whatever kind of cleverness that you manage, you realize that the wavelength is 1 meter and the frequency is 1 hertz, or 1 cycle per second. What that means is that every second one wave hits this pier, right? The part of the old broken down pier that's sticking out of the water. Now, how fast is the wave moving? What is the wave speed? Well, if the waves are 1 meter long and one of them is hitting here every second, that means the wave speed has to be 1 meter per second, right? And so we can immediately see that wave speed is frequency times wavelength. That concludes your exam review for this exam. I hope it's been helpful. Obviously, if you have any questions, please email me, and I will see all of you soon.